Hello and welcome back to our SerDes Basics class. In the previous video, we examined what happens to a signal as it travels through a real channel. We saw that the channel is not ideal. It behaves like a low-pass system, where high-frequency components are attenuated more than low-frequency components. As a result, signal edges become slower, waveforms spread out in time, and bits begin to interfere with each other. This creates intersymbol interference, or ISI, which is one of the primary limitations in high-speed communication. So this raises an important question. If the channel distorts the signal this much, how do we recover the original data reliably? In this video, we will answer that question by understanding what equalization is and how it works. Equalization is a set of techniques used to compensate for the effects of the channel. At a high level, equalization works by reshaping the signal so that after passing through the channel, it more closely resembles the intended waveform. Another way to think about it is this: the channel behaves like a low-pass filter, so we apply equalization to counteract that behavior. Ideally, the equalizer behaves like the inverse of the channel so that the combined response of the system is as flat as possible. This can be expressed mathematically. The equalization transfer function is the inverse of the transfer function of the channel. This helps reduce ISI, improve signal-to-noise ratio, and increase the maximum data rate of the system. Equalization can be applied in multiple locations within a SerDes link: at the transmitter before the signal enters the channel, and at the receiver after the signal has been distorted. Let's start at the transmitter. One of the simplest forms of equalization is called pre-emphasis, or sometimes de-emphasis. The idea is to modify the signal before it enters the channel. Pre-emphasis boosts the high-frequency components. De-emphasis reduces the low-frequency components. Both approaches help compensate for the channel's tendency to attenuate high frequencies. In the time domain, this appears as emphasizing signal transitions, making edges sharper before they go through the channel. A more advanced form of transmitter equalization is implemented using a finite impulse response filter, or FIR. This is often called feed-forward equalization, or FFE. Instead of treating each bit independently, an FIR filter adjusts each bit based on its neighboring bits. The filter is made up of taps, each separated in time by 1 unit interval. The central tap is called the main cursor. Earlier taps are precursors, and later taps are postcursors. Each tap has a weight, and the transmitted signal is formed by combining these weighted contributions. This allows the transmitter to shape the signal so that it counteracts ISI introduced by the channel. With enough taps, an FIR equalizer can significantly reduce both precursor and postcursor interference. Now let's move to the receiver. The first type of receiver equalization we'll look at is the continuous time linear equalizer, or CTLE. The CTLE is an analog filter that operates continuously on the incoming signal. Its primary function is to compensate for frequency-dependent loss. It does this by attenuating low-frequency components and allowing higher-frequency components to pass more strongly. In effect, it behaves like a high-pass filter. In the circuitry, this can be implemented as a peaking filter with a transfer function that contains a 0 and 2 poles. This helps restore signal edges and reduce waveform spreading. However, there is an important trade-off. Because the CTLE boosts high-frequency content, it can also amplify high-frequency noise and crosstalk. So while it improves ISI, it can increase noise sensitivity. Next, we have the decision feedback equalizer, or DFE. The DFE works differently from other equalizers. Instead of filtering the incoming signal directly, it uses previous bit decisions to remove interference from the current bit. As we've seen, the channel has memory, meaning previous bits affect the current signal. The DFE estimates this interference and subtracts it from the signal. As a result, the DFE can cancel post-cursor ISI very effectively, and it does so without amplifying noise. This is a major advantage over linear equalizers. However, there are also limitations. The DFE relies on previous decisions being correct. If an error occurs, it can propagate forward and affect future bits. So while it is very powerful, it must be used carefully. In more advanced systems, especially at very high data rates, another equalizer is added on the receiver side. This is the receiver feed-forward equalizer, or RxFFE. Like the transmitter FIR, this is also a multi-tap filter, but instead of shaping the signal before transmission, it operates after the signal has passed through the channel. One key advantage of the RxFFE is that it can compensate for both precursor and postcursor ISI. This makes it more flexible than a DFE, which can only remove postcursor interference. However, because it is a linear filter, it also shares the same limitation as CTLE, which means it can amplify noise along with the signal. In real systems, we don't rely on just one of these techniques. Instead, we combine them together to provide the best chance at recovering the signal. A typical equalization chain looks like this. At the transmitter, we start with FIR equalization. This is also known as FFE. At the receiver, CTLE is used to compensate for frequency loss. DFE is used to remove post-cursor ISI, and sometimes FFE is used for additional shaping. Each stage addresses a different aspect of channel distortion. When used together, they can significantly reduce ISI and restore the signal to a usable form. In fact, combining multiple equalization methods allows the system to recover signals even in channels with very high loss. Each equalization technique has its own strengths and limitations. The transmitter FFE is good for shaping the signal early, but limited by output amplitude and power. CTLE is simple and efficient, but amplifies noise. DFE does not amplify noise, but can introduce error propagation. Just a side note for this, there is a technique called forward error correction, or FEC. This isn't a type of equalization, but it is used to help recover incorrect data. It is used in extremely high-speed serial links and goes outside the scope of being in the basics class. However, I did want to reference it since it is very crucial when errors do show up, even when equalization is applied. Now back to the trade-offs, receiver FFE is flexible and powerful, but also amplifies noise. So designing a SerDes system involves carefully balancing these trade-offs. The goal of all these techniques is to improve the received signal. When equalization is applied correctly, ISI is reduced, signal edges become sharper, eye diagrams open up, and timing and voltage margins increase. This directly improves system reliability and reduces bit error rate. So while the channel introduces loss, distortion, and ISI, equalization provides a way to overcome these challenges. Channels will never be perfect, so we design the transmitter and receiver to compensate for its imperfections. By combining multiple equalization techniques, modern SerDes systems are able to operate at extremely high data rates. In the next video, we're going to build on this understanding and look more closely at how we measure signal quality using eye diagrams and bit error rate, and how engineers determine whether a system meets its performance targets.